9:30 class was canceled, but I was already here. And I was disappointed that you guys didn't show up. You guys knew more than me, but so anyhow, so today's class, obviously not everybody in section A can make this time. I recognize that, and so if you have friends, tell them not to be alarmed, right? So today's class is going to be just sort of a fun class, just to get to know one another, and the real will start from Tuesday next week. So let's do a few basic things. So the first thing that I do, the first day of class is give a quiz which is worth 50% of the course grade. That's what we're going to do now. Do you need, is my voice booming enough that everybody can hear it, or do I have to wear a mic? Oh, you want me to have, for the recording, okay. Oh, the other thing that I'm planning to do this semester, which I haven't done before, is I'm recording the lectures, the morning lecture. And so it'll be available on the web. So those who are missing the class today, they won't miss out on any of the fun. They can actually see the recording, okay. Did everybody get a copy of this? No, so this is meant to be a diagnostic. This is supposed to be things that you should know coming into the class, and so it's not going to count towards your course grade or anything like that. Don't be alarmed, despite what I said. Hey. Happy New Year. So how's things? So you must be.
I'm Matthew.
Hey, you exchanged some email, right? Yeah.
Sorry?
We exchanged some email,
Yes,
right?
How's it going?
Pretty good.
I've been stuck in airports the past 4 days.
So I got Kirak and MK to help me today.
Great.
With recording,
Fantastic,
right?
Yeah.
And so, but it's pretty straightforward, so you can learn what to do.
So yeah, we'll talk about it.
Yeah. So I'm right now giving them a diagnostic.
Okay,
This is the
cool.
first year diagnostic.
Yeah. All right. I have another class to go to. I just wanted to.
Yeah, fine.
Sure that,
That's fine. We're fine with this. From Tuesday, if we can start doing the recording in the regular class.
And we have a meeting at
11 on Tuesday.
Okay. Where?
Same room.
Okay.
1443.
Got it.
Matthew, what about you? Also have a class now?
No, I actually have a free hour here.
Okay.
But, your sections meet during a class that I already have. But
That's okay. So if at least some of you are here in my class, that'll be
yeah,
fine.
I can attend the other section if you want.
This one,
Lecture.
right? Yeah. It's up to Alenka. If she wants it, we can discuss.
Yeah,
Okay.
this is my first semester too.
Okay. All right.
You want me to just sit in the back? Sure.
No, why don't you help Kirak over there? Okay. On how to use the system. Yeah.
Well,
All right. Yeah. See you then. Yeah. Good to see you.
And should we grade these?
Yeah. Yeah. Right. So once I'm done with that, I'll give it to Matthew, and you can collect it from Matthew, right?
Yeah.
Okay.
Yeah.
2200, right? Mm-hmm. Matthew, after the classes, after the students return the papers, I'll give it to you, and you can then give it to Alex. Okay, all right?
Give them to him at a certain date or something.
No, we need to have that. It's pretty simple. I want you guys to get them graded before the next class so that I can give the summary. It's a diagnostic, so I want to do that on Tuesday. The results of this, okay?
Okay, so give them to Alex before Tuesday.
Well, today, tomorrow, if you can.
Okay.
All right.
I'll find him.
Just send him email and then find a place to give it to him.
Should I independent instructions to Alex or just?
Well, see, Matthew is not going to be able to make my class on.
I can change my schedule.
No, you don't have to do that. He has a class that meets at my class time, so he's not going to be able to record it. So Alex is the one that really needs to know how to do it. Okay.
Alex gave me an instruction.
Yeah, so he can just watch, but if he's available or something like that, he can.
When is Alex available?
He's available during my class time, but right now he has a class. So
Right now he's available.
yeah, so he has another class, and last 4 or 5 days he was stuck in airports. He just arrived.
Oh.
So maybe you can get together with him sometime tomorrow. To
Alright.
for Tuesday, if you can make sure that he knows how to do it, that'll be good. Okay.
I'm gonna buy a card, like in Korea.
We can get a card here, I think.
Yeah, I guess that's more, that's much easier.
Yeah, let's do that. Let's get a card.
Because every time we have something
No,
like
yeah.
this stuff.
Yeah, so let's do that. So let's find out. Don't we have a card in the lab?
Never seen before.
Okay, we can get a card.
Yeah, Danny has one, I guess, but that's her one.
Let's get a card. Okay.
If you're all done, let me know so that we can collect the papers. Anyone still working on it? Okay. If you're done, let me collect this. Thank you. Thanks. These are extras, right? Matthew, it may be easier for Alex to pick it up from me, I think, so I'll hold on to them.
You know me? I already sent an email.
Oh,
Yeah.
you're gonna hook
Yeah,
up with
if
him?
he responds in time, I'll be able to get to him today. And if not, I can probably catch him by tomorrow on Friday.
Okay, that's good. Excuse me. That's okay. That's okay. So how about we take 5 more minutes and then we stop, okay? And those of you who came late, if you want to finish it and then turn it into me later on, that's fine too, because it's a diagnostic, it's not counting towards any grade. So even if you want to do that afterwards and give it to me, that's fine, okay? Did you have a question? Was it your question? Okay. He's got it. So everyone done except the latecomers? Who's still working on it? Okay, good. If those who came in late, you can finish it later on and then give it to me. Okay. So what I wanted to do today is just talk a little bit about the course. Matthew, did you? Oh, you. Everybody know what the textbook is? Have a copy of that? Anyone have a copy of the book? Okay. There is it. So that's the textbook for the course, and so make sure you get a copy of that. And both the sections. And by the way, my name is not Alenka. My name is Kishore Ramachandran. I'm teaching the other section. So the for both the sections we will be using PRS, okay, and therefore it is important that you get a hold of a PRS unit if you don't have one already, so you have to get one. So those are two important things that you have to know, and what we have is you'll see that there are copious material online available for you, resources available in terms of slides and so on. And this semester, one of the things that I'm trying to do, hopefully it'll be successful, we're also recording my lecture, which will be the morning lecture. We're going to record that and we'll put it on the web. So those who, that doesn't mean you don't come to class, okay? So it is just meant as a way for you to refresh your memory later on. And let me, there is a, if I look at the performance of students in the class, there is a very, very strong correlation between good grades and class attendance. And so if you don't attend the class, I mean, there are some students who are super smart, who can read everything on their own and do everything on their own. So that might be one of you. It may be possible, but for I would say more than 90% of the class, it's extremely important that you attend the lectures, whether it is my lecture or Alenka's lecture. Make sure that you attend that because there is a strong correlation between your class performance and attending the classes. Okay, and it is a very intense course in the sense that it's a 4-credit course, and there is significant amount of project work involved, and the schedule is online, and you'll see that there is something due pretty much every other week, either homeworks or projects and so on, and we have recitations every week. Every Wednesday is your recitation in the evening, so that is something that is part of your schedule. Make sure that you don't miss those recitations. The reason why we have the recitation is because we want to make sure that you have the attention of the TAs at the time that you need it in order to do your homework or projects and so on, and so don't lose out on attending the recitation hours. Okay, and during the recitation hours there will be no new material covered. Okay, everything that we would have covered in the class, they may clarify that in the recitation hour, either to do your homework problems or in order to do your projects. Okay, and so it's extremely important that you attend the recitation hours. And let's see. So this gives you the complete schedule. So make sure that you are aware of what is due when. And one of the things, and all of you have used T-square for submission and so on. You know the quirkiness about T-square, right? Sometimes it eats your assignments, and so it is extremely important that when you submit something, you retrieve it and make sure that what you submitted is there in the system. Because later on, if you come and say, well, I did submit it, it is not there, there is not much we can do about that. To be fair to the rest of the class, not anything against you personally, but to be fair to the rest of the class. And therefore, it's extremely important that when you use T-square, you make sure that your submissions actually get in, and you have a ticket that shows that you've done that submission. Okay. Anything else that you have clarification regarding the schedule or anything like that? So roughly, concretely, we have 2 tests in the course and 1 final, and the dates for the tests are also in this schedule that you'll see online, and so make sure that you plan around that. Okay. Any questions? Yeah, Kirak? No, they should get the new version, that the version that what's your name? David pointed out, that's available in the bookstore. So that's the one that you're responsible for. Okay. So I don't know when Alenka plans to start on the PRS, but I'll be starting on the PRS probably from next Thursday. So by next Tuesday, all of you who are in CS 2200 section A should definitely have the PRS unit. We'll do a trial run next Tuesday, and from Thursday we will be doing and the PRS, again, it serves 2 purposes. One is you may crassly think that I'm doing it for class attendance. No, that's not the reason that I do that. The main reason I do that is because I use that as a way of reviewing some material. So I have some questions that I put out, and that helps you to sort of just get in sync with what was covered up until this point, and therefore it's important that you get your PRS unit, and it does count towards your course grade also. And somewhere in here, I don't think it is on this page, but you'll see the breakdown of the course grade into projects and homeworks and tests and class participation, and what we have is 5% of the course grade is a class participation, and class participation is not just PRS, at least for me. It depends on, Alenka may do it differently, but in my class I really want you guys to talk. Okay, I want it to be an interactive session. I don't want it to be a monologue. It's boring for me, boring for you, and therefore it is extremely important that you ask me questions, and so your class participation grade depends on not just the PRS, but also my familiarity with the students, and if you talk to any of your friends who may have taken the course from me in the past, they'll tell you that by the end of by the middle of the term, I get to know pretty much every student in the class, and therefore if I don't know you, that means you have not been showing up in the class. Okay, so make sure that you come to the class regularly. Any other question on the syllabus or just the course in general before we get to the first lecture? Good question. I think it is. They're all individual projects, if I'm not mistaken. Matthew, is individual projects, right? So this was you took it with the content. Okay. I have to check. Well, last time when I did it, I'm not sure. Let me get back to you on that. So we'll have that posted on the news group anyhow, not in the news group, but in the announcements. Okay. But I think the projects are done individually, but I'll confirm that. Okay. Any other questions? Okay. Let me give you, excuse me. you can have this. This is a questionnaire that I give on the first day. You can finish it and then turn it into me. Okay. Yeah.
So what's this main difference between the homework and the project?
The homework are problems that are conceptual in nature, but the projects are usually things that you actually code, and as a result of the coding, you may have to do some answer some questions that are related to what you observe in the results and so on and so forth. But it is really coding projects. So that's actually a very good question. So one of the things that this course is about. So this course, the title of the you know the number. What is the title of the course? Systems and Networks. So anything more that you know about the course? Anything more that you know about the course?
Well, it's basically you're going over the structure of a basic computer.
Yeah.
And stuff about like how to speed it up, and I think there may be some parallel programming stuff.
Okay, getting there. 2110 part 2. Okay. What is 2110? What did you learn in 2110?
Circuits,
Yeah.
assembly,
Yeah.
and safety.
Okay. So why do you say 2200 is 2110 part 2?
Because I assume it's a deeper analysis of those three things.
Well, more than that. So, but you got a good start. So somebody else had a hand up. Anyone know more about what this 2200 course is? So you said systems and networks. So what does systems and networks mean to you?
The system is a lot of individual pieces working together, and a network is those larger pieces communicating with each other.
Okay. So systems is he said, what's your name? Reed said that 2200 is 2110 part 2, right? And so 2110 is circuits, right? And C programming, and how does it relate to systems? Okay, good start. But systems obviously should mean more than that. Yeah, but
Maybe it's like a step higher in abstraction.
okay. Still, I'm not getting the answer that I'm looking for. But operating system. So when you say systems, when you say systems, it's not just the hardware. So when you say CS 2110 part 2, that sounds like it's another hardware course. This is not. This is a systems and networks course, right? Which means that we're going to look at the computer system as a whole. Okay, so you've got this box here, right? And so what we want to know is what is inside this box. Okay, what is inside this box is, of course, circuits are in there, but as this gentleman said, what makes this box tick is the operating system, right? And the system software that actually puts all these things together. So this course is really about this sort of integrated approach to both hardware and software. So you're right in one sense, Reed, when you said that it is CS 2110 part 2 is the fact that in CS 2110 also we sort of give you the interrelationship between C programming and the lower levels of the hardware, right? So there also we're bringing hardware and software together, and in 2200 we're also bringing hardware and software together, but at a much higher level of abstraction. That's what this gentleman said, right? That a much higher level of abstraction, and in particular what we're saying is, if you open up a box, what are the things that you're going to see inside the box? What are the things that you'll see inside the box? Because externally you see the user interface and you probably are looking at a browser, but what is inside the box? Processor, hard drive, display, then? A lot of other, what are the other things that you're missing? Important things missing. Memory, so peripheral interfaces, then? Motherboard is, it's just the processor on and other things on the board, but other things, well, what else are we missing? Pardon me? Graphics card. You said systems and networks. So what is the other part? Networks, right? So inside the process, to make this box interesting, the things that come together, there's processor, there's memory, there is peripheral devices, and different kinds of I/O, from graphics to disk to microphone and so on, and then your boxes. Today, your box is almost useless unless you can connect to the internet, right? What interesting things that you can do inside a box. So you want to connect to the internet, so network becomes an important part as well, right? And somebody else, you mentioned parallelism somehow, right? So why is that important from the point of view of this box?
Oh, well, if you have multiple processors.
Yeah. Do we have it inside the box?
Most of them have a dual processor.
So what does it mean when you say, when you hear this, it's a dual core?
You can run two different things at the same time.
Right. So when you say dual core processor, what does that mean? Pardon me? Two processors inside, right? So these boxes have become very powerful these days. Actually, even your PDA has become very powerful these days, right? So in that sense, a box contains multiple processors, and if there are multiple processors, then you need to understand, if you say that this course is about systems and networks, we need to know how these processors work together, right? And so that parallelism, parallel programming becomes important. So in terms of what this course is covering, it's covering these 5 units, right? The first unit is the processor unit, okay? And in the processor unit, one part of it is understanding what makes the processor tick, meaning what are the circuits that go into building a processor, how do you build a processor, and that's one part of it. But once you build a processor, then you sort of forget about it, right? Processor is a processor, it's going to execute a program, right? And so you can use an abstraction that says, here is the processor, and I'm going to use this for launching my browser or running my email and things like that. So you have multiple things that you want to do all on the same processor, so you have to schedule these applications, right, on top of this single processors that you may have, or even if you have 2 processors, and if you have 10 things that you want to do, you're limited in terms of computational resource that you have in that single box, and so that is the part that that connects the hardware and software, right? So there you have to schedule these applications on top of the processor. A piece of the operating system, that's my wake-up call. I'm awake. That's 5 points off for me. And by the way, if your cell phone goes off during my class, it's 5 points off. So 5 points off for me. That's a joke. So where was I? So I said that processor, you want to schedule it, and the piece of the operating system that deals with processor scheduling is what we'll study as part of thinking about this processor unit, right? So the hardware part is how to design the processor. The software part is how to schedule the processor when you have multiple things that you want to do, and because that is an interesting and important piece of the operating system. Okay. The second thing, somebody mentioned memory. Okay, and in some sense, memory subsystem is perhaps extremely, if not more important than even the processor itself. A processor, if you have a blazingly fast processor, if your memory system is not up to snuff, then you're not going to get the performance out of your system. So the memory system is extremely important component of your computer system, and that's the second unit that we'll look at. And once again, there is both the hardware part of it and there is the software part of it. The hardware part of it is, of course, the fact that you have memory chips that are put together, and what is the software part of it? Memory allocator, what do you mean by that? Right, so if there are multiple programs that you want to run, then you have to accommodate all those programs on the available memory, right? So then you have to worry about how do you divvy up the available physical memory among the competing clients for this memory, right? So that is memory management, and that is yet another piece of the operating system. That's one of the crucial components of the operating system. So that's the second thing that we look at, is the memory subsystem. And the third thing that we'll look at is the I/O component, right? And so you mentioned peripheral devices, and so in the operating system you have what you're doing is you're running programs, but every once in a while the interesting things happen when you interact with the program, and when you do that, then the operating system has to recognize that there is external events coming in, and so the I/O subsystem is caring about dealing with the interruptions that happen in the normal program execution. and also worry about connecting different peripheral components to the computer system. So that is the third component that we will subsystem that we look at, and when we look at that subsystem, we'll use one concrete example as a driver for thinking about I/O subsystem, and that is the hard disk. Because the minute I said, what is inside a box, you say, well, there is a hard drive, because the hard drive is holding all of your permanent storage, and that's important. Even if after you close the lid and go away, you want all of that stuff to be in the computer system. So the disk subsystem becomes extremely important, and so we'll talk about the both the hardware side of it and the file system side of it, in terms of how you build a file system on top of the disk. So that is the third component, and the fourth component is what you mentioned, that is parallel programming, right? Because you have multiple processors, and therefore if you want to be able to say that I understand systems, you want to know how to program multiple CPUs that may exist inside the box, and not just the programming part of it, but also what does the operating system need to do in order to manage multiple processor resources. So that's the fourth component, and then the fifth component is the network, right? And as I mentioned, your box is useless unless you can connect to the outside world. So then how does it in connecting to the outside world, there are so many vagaries that come in. Inside a box, you have control over it. The minute you connect to the outside world, the network may go down, the connection may go down, and so on and so forth. So you have to worry about all of those things, and that is what is called the network protocol stack, and that becomes another part of the operating system. So these are the 5 components that make up this course. Is that 2110? What did you call it? Part 2. Does it sound like that? Deeper than that, hopefully. So basically, this course is all about understanding what is inside a box. And once the thing is that if you think about processor, you think of Intel, right? If you think about the operating system, you may think about Microsoft or Apple, charitably or uncharitably, depending on your point of view. But the point is that you think of each of these things as something that is huge, right? So processor looks like, oh, how do you design a processor? Seems like too big a task. Similarly, how do you build an operating system? It seems like thousands and thousands of lines of code, right? But what I want to do in this course is sort of break it down for you, so that it becomes very simple for you to understand that, oh, these are just pieces that you connect together like Lego blocks. And so by the end of this course, you should have the confidence that, oh, I can build a processor, I can build an operating system. Okay, so that is the kind of thing that I'm expecting that you'll get out of this course. And one of the things that used to happen in our curriculum, going back about 12 years, is that we used to teach hardware and software separately. Okay, there used to be a course that separately teaches architecture, and there's a course that separately teaches operating systems, and we used to be on a semester in a quarter system, and typically a student may take an operating systems class in one quarter, and then an architecture class in another quarter, and they never see the connection between the two. And already you can see from what we discussed today, the connection, right, between the hardware and the software. So one of the important intent of this course is that that connection is apparent to you, and something that you carry forward from this course. And that's the reason that we switch between talking about processor hardware, and then we talk about how to schedule the processor. And similarly, we talk about the memory subsystem from the hardware point of view, and then the memory management that the operating system has to do, and so on with every one of these units. That's what we do, so that you can always see that symbiotic relationship between hardware and software. And that's the goal. And if I'm not delivering on that goal, you should challenge me, right? Or you should challenge Alenka if you're not delivering on that goal. So that is the goal, to make sure that you get this connection. And once you have that, how many of, this is a strange question, and I'm scared to ask this question, but how many of you are in this class because you love systems? You love systems and you want to learn everything about what is inside the box. How many of you are in this class because of that? How many of you are in this class because it's a required course, you just had to grind through it? how many of you, you're also late okay, well, how many of you are here because you wanted to major in computer science or computer engineering? I mean, you're all here, right? I mean, why are you here if you did not want to be a computer science or computer engineering major? Are all of you here because you want to major in computer science or computer engineering? Anyone here because they don't really care about computer science or computer engineering, but they just decided that they'll come and sit in my course? I hope none of you are like that, right? So if your major is computer science or computer engineering, regardless of what you want to do in life, whether you want to be a graphics designer, a graphics programmer, or you want to be an HCI programmer, it doesn't matter what you want to do. You need to understand this sort of symbiotic relationship between hardware and software. And so my goal always is, I mean, every time I teach this course, I ask this question, and my goal is by the end of the semester, I want to have more converts who say, well, I really love systems. So we'll see if that happens. Any questions so far on what the intent of the course is? And what we do in this course in order to, you know, and you asked a question, what is the difference between homework and project? One of the things that always happens is that you know, these concepts, I can talk about it until you go blue in class, and you can read about it, but unless you get a project done, you don't really see the sort of there's an aha moment that comes when you do the projects, and that's the reason that you know, in this course we have 5 projects that dovetail the 5 components that I mentioned, and those projects actually make the concepts that you learn in the course come through to you more clearly. Okay, and so, you know, and the other thing that I want to mention is we space these projects. If you see, you know, the projects are all very well spaced out from one project to the other. So you release, we have the first project that we will release in the second week, that is next week, and then that is due. Let's see, when is it due? So this is the due date, right? So the project is due here. So we typically give about 2.5 weeks between the time that we make the project available to the time it is actually due. Start on them right away. Don't wait on them till the last minute, because if you wait on them, I mean, these are significant projects, and if you wait on them, you're never going to get done. Okay, and so it's important that you don't wait on them, but get started on them right away, and that way you can keep up with it. And another unpleasant thing that I have to mention is, you know, we come down very hard if students are not honest, because a lot of students are extremely honest. Most of you are extremely honest, and therefore we want to make sure that nobody is, I mean, the honest students are not penalized by students who cheat, and therefore we come down very hard on students who cheat, and therefore don't even think about it. And you're all very smart, I mean, otherwise you wouldn't be here at Georgia Tech, right? So use your smartness to do the projects and the homeworks by yourself, and doing it well. Okay, and it's an unsavory thing that I have to say every time I teach this course, but I have to say it. Don't, you know, be honest, and you'll do fine. Yeah, read. Well, so this is a good question. So what is the collaboration policy? The collaboration policy is very simple in my mind. Okay, and the collaboration policy is you can talk to your student, to fellow students, discuss how to do problems. You know, I encourage you to do that. Similarly, you know, if you have a programming project and you want to think about how to do it, think together. There's nothing wrong with collaborating in terms of exchanging ideas, exchanging thoughts, and so on. But when it comes time to do the project, then you are by yourself, right? You're not taking somebody else's code and putting it into your project and turning it in, or you're not getting it from the internet and putting it in your project and turning it in. But, you know, collaboration, I mean, I think all of us learn by talking to one another. So I fully encourage collaboration in that sense, right? But there is a fine line between collaboration and cheating. And if you're not, you know, absolutely certain, come talk to me. Okay, you know, I'll tell you if you are crossing the line or not. Okay, but I do want you to definitely take advantage of you know, your fellow students, TAs, and instructors to ask questions and share ideas on how to do things and so on, because in the real world that's how you learn, right? So if you're going to be, if you're going to go to work, you're not going to be doing everything by yourself, you're going to be working with others. So in that sense it's perfectly fine for you to collaborate with one another in learning, in sort of unraveling how to do a problem and things like that. But when it finally comes time to do your work, your project or your homework, you do it yourself. Okay, is that clear? Any questions on that? That's a very good question, thanks for asking that. Yeah.
We've been like boot camps for the last 3 days, so is there going to be any delays in the schedule? Classes?
That's a good question again. Well, I don't know. We may. I'll talk to the TAs about that and try to see if we can space it out a little bit more. See, the thing is, the first homework we're releasing only on Friday, that is tomorrow. Okay, and that first homework is basically getting you familiarity with the simulator that you're going to be using. So in that sense, there is not course material that comes in as much as exercising the simulator. So I don't think that will hurt you too much. But there is a danger in sort of letting the schedule slide because there's too many things that are stacked up one behind the other. So we'll think about that, whether we need to do that or not. But I don't think at this point there is any need to do that. As I see it, we are probably behind by one lecture, but we can make that up. Okay. So at this point of time, let me say that there is not going to be any change in the schedule, but if there is a need for that, I'll talk to the TAs and then get back to you. Okay. Any other questions? Okay, so what I want to do is, let's see, the remaining time that I have, I'm going to just walk through a few slides to sort of understand, what this course is all about. I already mentioned some aspects of it just as we discussed just now, but we will take a few minutes just going through these slides. So in terms of somebody mentioned abstraction. So who was that? You did, right? What's your name? Pratik. Yeah. So you mentioned abstractions, and so this is the abstraction hierarchy, right? So at the lowest level you have solid state physics. How many of you have taken, all of you must have taken physics 101 and so on and so forth, right? So you've learned about the chaotic thing that happens inside with electrons and holes and things like that. But out of the chaos comes transistors, right? So this is an abstraction, and at this level of abstraction you're able to think, don't have to worry about all of these electrons and holes, right? Because you can think in terms of switches, on off switch, right? And the on off switch is really working because of all these solid state physics that is happening under the covers, but you don't care about that, right? At that point you can forget about it and say, well, I just have transistors, switches that I can deal with. That is one level of abstraction. Now if you move up a level, you have logic gates. That's AND gates and NAND gates and so on, which you saw in 2110, right? So that becomes a way by which you can actually express logical equations. You all know what the difference is between sequential logic and combinational logic. What is sequential logic? What is sequential logic? Oh, what is combinational logic? Let's make the simpler question first. What is combinational logic? What is combinational logic? Pardon me?
I was going to say sequential logic would be like more like cause and effect.
Wow, you're using abstract philosophical terms here. So what is combinational logic?
Would it be sequential as like an if-else type thing? Combinational as like and or...
Okay, but can you give me in terms of anything that you know about everyday life, whatever you know about, what is a combination logic? What is an example of a combination logic? Time sequential, right? What is combinational? Pardon me? A lock, right? So you put some of these things together. So the key thing that a combinational logic lacks, that is in a sequential logic, what is that? State, right? So you don't have the minute you add state to it, then it becomes sequential logic, right? So combinational logic is, I'm going to pick up this piece of paper and then keep it here, right? So this is, well, I've not done anything that remembers anything. Now if I remember that I kept it here, when I come back and then take it from here and then put it somewhere else, that is sequential logic, right? So that is giving you, as Reed said, there's a time step to it, right? And it need not always be there, but it could be there. But the important thing is there is state associated, right? There is state associated with the actions. So it is not just, if I'm watching, like if you're taking a video over there, right? So every frame of video that is coming in is like a sequential logic, because every frame is unrelated. So every frame is a frame by itself. But if I want to say that, well, what happened at 3:25, right? Then you're asking for a state that you can remember at that point of time to retrieve something, right? So in that sense, the state is the main thing that differentiates combinational logic from sequential logic. And so one of the nice things once you have the abstraction of a logic gate is that now you can express a sequential logic, a combinational logic circuit with the gates, right? So you can actually say that if this happens and this happens and this happens, a combination of that will result in some final event that is being triggered, right? So that is the way you can build combinational logic circuits. And if you add state to that, how do you add state to that with in building a logic circuit? How do you add state? Flip-flops, right? So flip-flops is a memory element that remembers the old state. So you can use that to actually drive the output, and that becomes a sequential logic circuit. And so using these logic gates, you can build sequential combinational logic elements. Okay, if I give you an adder, you all gave in the questionnaire I said there's an adder. Is that a sequential logic element or is it a combinational logic element? It's combinational because it is just taking the set of inputs and then computing something, right? Doesn't know anything about past. It doesn't know anything about the future. So it's a combinational logic circuit. But on the other hand, if I say that there's a program that is contained in memory and it is going to execute one after the other, instructions one after the other, that's a sequential logic, right? So you can build all of these sequential combinational logic elements using these logic gates, right? So that becomes yet another level of abstraction, right? So once I built, let's say, an adder, then I don't have to worry about how many gates that are contained in the adder and so on, right? Because then I can use that adder in a higher level circuit that I want to build. Okay. Similarly, in 2110, you may have learned about multiplexer and decoder and things like this. These are all circuit elements that you can build out of basic logic gates. Once you've built them, you can forget about the logic gates. You can think simply in terms of, I want a multiplexer here, I want an adder here, I want a decoder here. So you can put those higher level circuits in order to build a larger, as you mentioned, motherboard, right? So motherboard is nothing but a data path that connects together all of these different logic elements, okay? And some of which may be sequential, some of which may be combinational, but the combination of all of that gives you the ability to do something big like a processor, right? And so that is this level of abstraction. And moving up one level is the machine organization. That is, if I say, well, I want to build a processor, then in order to build a processor, then you need certain logic elements, and you have to connect them in certain ways, and that's where the data path and control comes in. And moving up a level, you have the computer architecture, and that is saying, well, this is an Intel processor, or this is a Spark processor. Okay, so each one of these processors is going to have its own. What is distinguishing, say, an Intel processor from a Spark processor? Architecture. What do you mean by the architecture? Instructions, right? So the instructions is what is distinguishing one processor from another. And so as an architect, I might say this is the instruction set for my processor. Okay. Once I decide what the instruction set is, then I can say, well, how do I design the machine that implements that particular instruction set? So that's where the machine organization comes in. What is the data path? What is the control? And we will see this in the next lecture when we talk about the processor. And moving up the level, if there are system software. So what's your name? No, this guy. Joe. So Joe mentioned systems, right? So when we say systems, we are combining architecture and software elements, and system software elements in particular. And system software, you've already been using things like compiler, operating system, and so on, right? And so though the combination of the system software and architecture is what makes it a computer system. And so at this level of abstraction, you could say, well, I don't care about the data path and control. All I want to know is, for a compiler writer, what does he need to know? If I'm a compiler writer, what do I need to know in order to go from, say, the higher level language, it may be Java or C or whatever, to things that run on the processor? What do I need to know? Pardon me? No. You need the instruction set, right? So all you need is the instruction set, because once I know the instruction set, I can take a higher level construct, if there is a construct like a procedure call, and I can say what are the instructions that I need to execute in the processor in order to give you that for the user the feeling that you executed a procedure, right? So in that sense, the compiler writer, the only thing that he or she needs is the instruction set. You don't have to worry about the data path and control, you don't have to worry about sequential logic elements or anything like that, right? So that's the beauty of building these levels of abstraction. So once I built this level of abstraction, then that becomes a contract between the compiler writer and the architect, saying that this is the instruction set. Then once I've decided the instruction set, the architect can go off and build a processor, right? And the compiler writer can go off and write the compiler, and then you can come back together later on to make sure that it all works together. And the same thing goes for operating system. And then moving even one level up, you have, you may be taking courses in graphics and courses in high performance computing and so on, and you're writing algorithms, right? And you're writing algorithms at that level of abstraction. You don't even care about the compiler or the operating system, right? You may not even care about a language, right? Writing an algorithm, it's just stating what are the sequence of things that you want to do in that particular algorithm. Let's say if the algorithm is doing a matrix multiplication or something like that. So you're just saying what are the steps involved in that. Then you go to the next step of saying, well, let me code it up in a particular programming language, right? So the algorithm is yet another level of abstraction, right? So all of these are different levels of abstractions in the computer system, which makes it, that's one of the things that makes computer science that much exciting, that we can abstract out the details when we don't need them, and we can look at the detail when we need them, right? And so in this course, our focus is going to be on the shaded part. Okay, so Reed's point about CS 2110, right? That was dealing with this part of it plus C, right? And so we moved up in the food chain, and we're going to look at this level of abstractions in this course, and we're going to cover the 5 components that I mentioned in doing this course. Okay, and so these are some pretty pictures. And what is this? Can you say what this is? Google Earth, right? So you're using different applications, and you can simply move your mouse over it, and suddenly it expands and contracts and so on and so forth. What are the things that are going on inside when it happens? So if you click on it and then you blow things up or contract it, what is going on? Read.
You talked about abstracting each level off.
Yeah.
If you didn't want to abstract it, could you build hardware for software? Is that
What do you mean by that?
like if you knew you had a particular program to run and this computer was only designed to run that program, could you build hardware from the ground up to run it?
Oh, you can do that. There is that's an area called silicon compilation. So you can actually go from an algorithmic specification and you can make application specific processors. Okay, so you can do that. But in this course at least we're going to be talking about general purpose processors, because that's the bread and butter of companies like Intel and so on and so forth. But definitely you can actually there are especially in the area of digital signal processing, DSPs, you can actually go from an algorithm specification down to the silicon and build a processor specifically to do that. It won't do anything else, but it'll just do that. And one of the downside of doing something like that is because it's going to be very specialized, right? And it'll be very good at the time that you build it, but technology continuously moves, right? And so commodity processor may be faster than the special purpose processors that you built, because there are more people working on the commodity processor than a special purpose processor. And so this is one of the things that has happened over time, is that there were companies that built special purpose processors, but given that how long have you had this box?
Bought it last Christmas.
How long do you expect to have it? Another year. Yeah, see, so 2 years, right? So there is the lifetime of a box is pretty small, right? So continuously there is new technology that is coming in, and so if you build a special purpose processor, you have to have the workforce to continuously update that special purpose processor. That's why commodity processors have become so fast that you have to really think hard whether you want to build a special purpose processor, but it is possible. Okay, so it's not something that. No, coming back to my question, I was asking, if you open up Google Earth and then you click on it and then magic happens on the screen and so on. What is going on inside the box? What is going on inside the box? And similarly, if you play a video game, right? If you play a video game and what is this game? So if you play this game and shoot at objects and so on and so forth, magic happens. But what is exactly going on inside the box to do that? So one thing that I mentioned is this connection between the compiler and the instruction set, right? So if you think about the video game, there is video and audio content that is part of the game, and then the program itself. So I mentioned that the high level, you write the algorithms for shooting an object and things like this, and all of those algorithms are going to be converted into source code, and then you give it to the compiler, and the compiler is going to say what is the instruction set, and I'm going to compile it to that particular instruction set. So this is the software stack here, and this is the hardware stack, right? And you can see that the only thing that the software guys need to know about is the instruction set. Rest of it is all magic. They don't have to worry about that, right? And so that gives you the video game. So this is the connection between, or the relationship between hardware and software. But what about the operating system? Where does that figure in this picture? Where does the operating system figure in? The compiler is pretty easy to understand, right? So write a program in high level language, compile it, and in order to compile it you need to know the instruction set, and that's where the relationship is between hardware and software. What about the operating system? So one thing that the operating system is doing is it is worrying about what programs to run at any point. And if you think about the compiler, what is the compiler? It's also a program, right? It also needs a processor to run on, right? And if you have the video game, that's also a program that needs a processor to run on. And so in the operating system plays a pivotal role in sort of doing this resource allocation across. So this is more detailed than what I want. So the operating system is a resource manager, right? So it is providing consistent interface to the resources, and as you mentioned, it is doing job scheduling. If there are multiple things to run, it is deciding what to run at any point of time. And in the case of the Google Earth, if you click on the mouse, okay, the operating system has to recognize that, oh, you clicked on the mouse, and therefore you want something to happen. And what needs to happen is decided by the application program. In this case, the Google Earth is going to decide that, but the operating system is the first guy that gets that and then passes it on, right, and to the particular program that needs to react to that, right. So all of those things is what the operating system is orchestrating, and so I'm going to skip this. So this is actually showing what might happen in a distributed system. So if you start from here, if you click on the mouse, the operating system first recognizes that there is a mouse click, and that's on the client side, right? And then the client has to then pass it on to the server, because the server may have the game logic of what is going on with all the players and so on. And so the server gets this message, and this is where the network comes in, right? So if the server is remote, the network comes in, so you send the message over to the server, and the server then sends it to the client, and the client side operating system has to receive that message and then figure out, oh, this is intended for that particular client, and it's going to pass it up the food chain to the particular client, and then magic happens, right? So all of these things are happening instantaneously for you, but under the covers hardware and software are coming in order to make it all happen. And what we're going to do in this course is actually understand all of these pieces together, because one of the things is that a processor, what is the processor doing all the time? What is the processor doing all the time? What is it doing? What is it doing? What is the processor doing all the time? Well, more than that. What is the processor? Somebody said architecture is instruction set, right? All the time, all the processor is doing is just running instructions. It cannot do anything other than run instructions, right? And therefore, but I'm not pointing the. Oh no! What? No. See, the laser is over here, so it cannot be. Oh, sorry. I'll leave it here. So the processor, all it can do is run instructions, right? And now if I click on the mouse, what am I telling what am I doing at that point? When I click on the mouse, what is going on under the covers? What do you mean by interrupt?
Interrupts whatever instruction.
Right. See, the thing is, the processor is running instructions, right? So that is the only thing it is capable of doing, and an interrupt is like a doorbell. If I'm talking continuously, somebody knocks on the door, I'm going to go out and see who's there, right? And that's exactly what the operating system has to do, is grab control of the processor, because the processor is dumb, right? It can only run instructions. You have to tell the processor, shut up now, I want to go out and see what is going on, right? So in that sense, you have to stop the processor from executing whatever instructions it is executing, so that it can then go and then look at who's at the door, right? So going and looking at the door is yet another program, right? So just like we had the original program running, an interrupt comes in, you go off and run some other program, and that some other program is going to the door and seeing who's there at the door. And once I find out that somebody is at the door, and maybe the guy has come to visit Kirak, I'm going to say, well, I'm going to deliver that message to Kirak, right? The operating system is going to tell Kirak, oh, there's somebody to meet you. So that's what the operating system is doing, is sort of mediating between events, external events and internal events. Internal events, a processor is executing continuously, and external events are interrupts, right? When interrupts happen, you react to that and then pass it on. Okay? And that's exactly what this picture is showing, is all of that sort of complexity. And so what we're going to see in the course is this relationship. And I'm going to show you one more slide and then quit. So this picture is a picture of an ancient computer. Okay, it's called the ENIAC, which is the very first computer that was built. Okay, built at University of Pennsylvania in 1940s, and it had on the order of 18,000 vacuum tubes, and it occupied a room that is as big as this in terms of all the components that sat inside. And you know the processing power of this computer in today's terms? In today's terms, what will it be? Is it, pardon me? Pardon me? A rock? No. Oh, calculator? Very basic calculator. You've seen Hallmark greeting cards? The processing power inside that. There are the singing greeting cards and so on. That's the processing power of this machine right here. Okay. So we've come a long way, and so we're gonna see, and it cost millions of dollars to build it. So we'll stop here, and so those of you who are in the afternoon section, enjoy, and those of you who are in my section, we'll see you on Tuesday. Okay. So all of the material that I talked about today is the first chapter of the book.